So a squash ball is released from rest at a height h above the ground. So let's draw a diagram. We have a squash ball which is at a height h above the ground. Let's draw the diagram. And it is mentioned that at each bounce, 75% of its kinetic energy is lost to the surroundings. We need to find what is the height reached by the ball after its second bounce. So how do you approach such questions? First of all, let's draw a diagram and let me label A is the original position of the ball when it was at a height of h above the ground. So when it is released from rest, initial speed is equal to 0, and then the ball starts to travel downwards. Eventually it is going to hit the ground, let's say at the point B, and then it goes back up until it reaches another maximum height. Now this height will not be equal to the original height because the kinetic energy is lost to surroundings. And let's say this height is h dash. So this is the height of the ball after the first bounce. Now the question was to find the height after the second bounce. So let us try to find h dash first. And how do we do that? Using the law of mechanical energy conservation. But there is a catch. Remember, mechanical energy is conserved only when conservative forces are present. So till the time the object, the ball, is only under the influence of the gravitational force, we can apply the law of mechanical energy conservation. But notice, when the ball makes an impact with the ground will provide a impulsive normal reaction to the ball. And just to clarify, let me draw a diagram. Let's say the ball impacts the ground. So the ground will give a normal reaction in the upward direction. Now, normal reaction is a non-conservative force. So mechanical energy conservation will not be applied if we are considering this normal reaction. Now, to tackle that issue, what we will do, instead of B, which is the impact point with the ground, we are going to consider a point just above B. Let's call that as point C. So C is the position of the ball just before hitting the ground. And let's say the speed of the ball at that point is, let's say, V. So let me repeat. V is the speed of the ball just before hitting the ground. So from A to C, we can consider the only force acting on the ball is only gravitational force, which means we can apply the law of mechanical energy conservation. So let us equate the energy of A with energy of C. Now at the point A, the object was released from rest, so we can write kinetic energy at A will be 0 plus potential energy of the ball at A is mgh. So let's write that down. Now at C, C is the point just close to the ground, so we will consider the potential energy of the point C to be approximately 0 plus kinetic energy at the point C will be half mv square, where v is the speed of the object just before hitting the ground. And let's simplify this. We will get mgh comes out as half mv square. So basically this half mv square is the kinetic energy of the object just before hitting the ground. Now, in the question, it is mentioned after each bounce, 75% of the kinetic energy is lost to the surroundings. Let us label one more point in this diagram. So, we have considered point C, which is the position just before hitting the ground. Now, let us consider a point D, which is just after hitting the ground. So, at point D, the ball is moving upwards with, let's say, a speed of V dash. So let me repeat, V dash is the velocity of the ball just after hitting the ground. Now we are going to consider this point D until it reaches the maximum height. So let's say point E is the position of the ball when the ball reaches the maximum height after the second bounce. So from D to E, we can apply the energy conservation. So let us repeat the same principle. Earlier we applied the energy conservation from A to C. Now we will apply the same steps for D to E, where D is the point just after hitting the ground. So at the point D, we are going to consider potential energy to be approximately 0 because point D is close to the ground. And let's say kinetic energy of the ball at the point D will be, let's call this as KD. Now at the point E, which is the highest point, kinetic energy will be 0 and potential energy will be mgh dash. Now, in the question, it was mentioned that after each bounce, 75% of its kinetic energy is lost to the surroundings. And earlier, we had figured out this is the kinetic energy of the object just before hitting the ground. So let me write kinetic energy before hitting the ground is equal to half mv square, which is also equal to mgh from the law of conservation of mechanical energy. Now, kinetic energy after the bounce, what will that be? In the question, it is mentioned 75% of the energy is lost, which means 25% energy is still left. So kinetic energy afterwards will be 25% of the before kinetic energy. 25% will be written as 1 by 4, and before kinetic energy is half mv square, which is equal to mgh. So we'll write mgh here, which means the kinetic energy after hitting the ground is equal to mgh divided by 4. Now, if we go back up at the point D, which is the point just above the ground, kinetic energy at the point D will be equal to this mgh divided by 4. So let's write, instead of kd, we will write mgh divided by 4. That will be equal to mgh dash. And now let's simplify this. Mg will get cancelled out, and then we will get the expression for h dash as h divided by 4. And what was h dash? H dash was the height of the ball after the first bounce. So let us repeat the entire motion of the object. So the ball started from a height h, it hit the ground, it bounced up until it reaches the point E, and the height of the point E was h dash, which we have figured out was h by 4. So initially the height was h, but after the bounce, after the first bounce, the maximum height is h by 4. Now the question was to find the height after the second bounce. So let us now summarize. Initially the height was h, after the first bounce it went to h by 4. Now we can just generalize from h by 4 after the second bounce what is going to happen. So if you analyze this, after the first bounce 1/4 of height was left. Similarly here, after the second bounce we will say 1/4 of h by 4 will take place, which means h upon 16. So just to elaborate, let me draw a diagram. If the squash ball is dropped from a height of h, it is going to bounce up with, let's say, a distance of h by 4, and then it goes back down. After the second bounce, it goes back up by a distance of h by 16. Now the question was, what is the height reached by the ball after its second bounce? It is h by 16, which is option A. And now let us summarize what we have learned so far. Apply work energy principle when resistive forces like friction, air resistance are present, and this is the principle. The total work done by all the forces acting on the object should be equal to change in the kinetic energy. On the other hand, when resistive forces are absent, so non-conservative forces are absent, in that case, we will apply the mechanical energy conservation, which is simple. Initial energy needs to be equal to the final energy. And then we discussed how to figure out the work done by the conservative forces. So this is the formula for work done by the gravitational force and work done by the spring force. And let me write down the basic formula. Work done by any conservative force will be equal to negative of change in potential energy. So in case of gravitational force, the U will be GPE. For springs, the U is EPE. So, mechanical energy conservation is applied when non-conservative forces are absent. That's when we do initial mechanical energy equals to final mechanical energy. But here is the catch. We can apply mechanical energy conservation even when non-conservative forces are present. And how is that possible? We can apply mechanical energy conservation in the presence of non-conservative forces if the work done by those particular non-conservative forces is zero. Now, earlier we had taken this example of an inclined plane where object was released and then it slided down the inclined plane to reach the final velocity v. So we had used the principle of mechanical energy conservation to get the final velocity. Similarly, we had done another example where a pendulum was swinging and we had figured out the velocity of the pendulum at the bottommost point. So in the first case, the inclined plane, if you observe what are the different forces acting on this block, first will be the mg, the weight of the object acting downwards, and then we have the normal reaction, which is a contact force. Now, normal reaction is a non-conservative force, but still we used mechanical energy conservation to get the final velocity. How were we able to do that? The reason is, even though we have a non-conservative force here, the work done by this force is zero. Work done by normal reaction is actually zero. And how is that? Because work done is Fs cos theta. So let me write down the formula for work. The basic formula for work is F into S into cos theta. Now the force involved is normal reaction. S stands for displacement. Since the block is sliding down the incline, so I can draw an arrow. This will be the direction of displacement. And now we can see the angle between displacement and normal reaction is 90. cos 90 will be 0. Hence, we can say that the work done by normal reaction is equal to 0. Using the same logic, even in the pendulum case, we had used the mechanical energy conservation. So let us observe what are the forces acting on this balls, mg weight acting downwards, and then we'll have the tension T acting along the string. Now, even in this case, the work done by tension is equal to 0 because work is Fs cos theta, force is tension. Now, displacement in circular motion, to figure that out, all we need to do is just draw a tangent to the circular arc. So watch, let's say this is your circular arc. So all we need to do is just create a tangent. This will be the direction of displacement, and the angle between tension and displacement is 90 degrees. Again, cos 90 is 0, so work done by tension is equal to 0. So to summarize, we can apply mechanical energy conservation even in the presence of non-conservative forces, but those cases are very specific in the fact that work done by all those non-conservative forces should be 0. If the work done by non-conservative force is not 0, for example, in case of friction, then we cannot apply mechanical energy conservation. And based on this, let's try to solve a question.